Hey all you cool cats and kittens, and welcome to Properties of Exponential Graphs. So let's start off with the problem. So if you remember the Lorax from the Dr. Seuss books, suppose the amount of tuple trees in the Lorax's forest is modeled by the equation t equals 1250 times 1/6 to the d power. Okay? Well, if you remember the story of the Lorax was desperately trying to save the truffalo trees. So how many trees were in the forest to start? And if the Lorax did nothing at all, what would happen to his forest after many, many, many days had passed? In other words, the Lorax was like, screw this, I don't want to do anything. What would happen to his beloved tupelo trees? So as you can see, the question is, well, how could the Lorax just know without having to graph or make a table how many trees are in the forest to start? And what will happen to his forest? So as you know, the Lorax is a naturalist. He doesn't look like he uses a Chromebook. He doesn't look like he uses a graphing calculator. I mean, he doesn't even wear pants, for crying out loud. So how could he just know by kind of eyeballing this equation how many trees are at the forest to start? Hey, that is modeled by the y-intercept of the graph. So if we knew how to quickly eyeball the y-intercept of this thing, we could solve his problem. Also, what will happen to his forest after many, 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 many days? Hey, if we could figure out the end behavior of this, in other words, in this function, sorry, not x because we're using d for days, as his days goes to infinity, what happens? As d gets really, 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 really big, what's going to happen to his forest? So if we could figure out those two things, and if the Lorax could figure out those two things, he could just eyeball this equation, he could already know. So what we're going to learn how to predict the end behavior of exponentials because, duh, the Lorax, and the y-intercepts of exponential graphs, because again, gotta save tuple trees. So let's examine some patterns here to start, and maybe we can get an idea. So if we look at negative 2 to the x power, and we look at the graph looks like it's really, 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 really small, and then it gets really large negative. So as x goes to infinity here, the function goes to negative infinity, right? Because we look it to the right. And as x goes to negative infinity or to the left, the function looks like it goes to 0. Interesting. Okay. Let's do the same thing for 2 to the x. So here, as x goes to infinity, our function also goes to infinity. And as x goes to negative infinity, in this case, our function goes to 0, right? Flat lines out at 0. Okay, interesting. What's the only difference between these two equations, or these two functions? This one has a negative, and this one does not. Notice they're also mirror images of each other over the x-axis, right? This one goes up, this one goes down. Goes to negative infinity, goes to positive infinity. Interesting. Okay, what if I throw a fraction in the mix? Okay, well, looking at this graph, as x goes to infinity here, the function goes to 0. As x goes to negative infinity, the function, so negative infinity, read it to the left, the function goes to positive infinity. Okay, so as x gets large, the function gets really small. As x gets really large negative, the function also gets very large, but very large positive. Okay, interesting again. What about now negative 1/2 to the x power? So let's read the graph. As x goes to infinity, the function goes to 0. We're flatlining out on the right. As x goes to negative infinity, the function goes to also negative infinity, just kind of drops off. So again, this function and this function are mirror images of each other over the x-axis. And why is that? It's because of the negative sign. So that's exactly what the negative signs do. If you have a negative c out here, then your graph is going to reflect over the x-axis. So see, this one goes down, whereas this one goes up. This one is up, where this one is down. Okay, so the positives live in the positive, the negatives live in the negatives as far as the y values go. Okay, so if you're positive, you're in the top half of the graph. If you're negative, you're in the bottom half of the graph. Okay, but notice the end behavior is the same except for the negative, right? This end behavior, this went to negative infinity, this one went to positive infinity, and there is no negative 0, so 0, 0. This end behavior went to 0, this one also went to 0, because again, no negative or positive 0. This end behavior went to infinity, this one went to negative infinity. Alright, so we can deduce by this that exponents, exponentials, they make big numbers, or numbers greater than 1, bigger, and they make small numbers, or numbers smaller than 1, smaller. So exponentials make big numbers big, and they make small numbers small, whether they're negative or positive. That's the gist of this. So let's see something else. Okay, what if I have this plus 3 in here? So the graph of negative 2 to the x, that's this green here. This is negative 2 to the x. The blue is negative 2 to the x plus 3. Oh, what's the difference? Oh, it's a vertical shift of positive 3. All the points have been vertically shifted up by 3. That's all that's going to do. What's the difference between 1/2 x and 1/2 x minus 1? Oh, well, this here, the black graph is 1/2 to the x. The green graph is 1/2 to the x minus 1. What's the difference? Oh, a down shift, or a vertical shift of negative 1. All the points got shifted down. So these numbers hanging off the back do what they always do. They're always a vertical shift. If they're positive, the graph goes up. If they're negative, the graph goes down. So let's see some like official properties here. So remember the c times a to the x. Well, if c is greater than 0, this is saying if you have a positive out in front, well, if a is bigger than 1, so in other words, we're going to make big numbers big, small numbers small. So as we go to the right, we're going to grow. As we go to the left, we're going to shrink. So to the left, we go to 0. To the right, we go to infinity, because a is greater than 1. This is something like 2 to the x. Big numbers get bigger. Now, if a is between 0 and 1, exponentials make small numbers smaller. So we start up and we go down. As we go backwards, we go up. This is something like 1/3 to the x. Over time, as you keep cutting, you'll get small. This one is doubling, so you get big. So you're either doubling, tripling, quadrupling, or you're cutting, and getting really small. So exponentials, small numbers get smaller, big numbers get bigger. And the other thing then is, okay, well, what about if c is less than 0? These are reflections. Reflections across x-axis. Okay, so that's the difference between 2 to the x and negative 2 to the x. It's the difference between 1/3 to the x and negative 1/3 to the x. That would look like this. That would look like this. They're just mirrors of each other. Alright, and what about the ever so infamous y-intercept? All you do is plug in 0 for x. That's always, right? If you want to find the y-intercept of anything, anytime, always in math, just plug in 0 for x. So that's all you have to do. Alright, let's now look at some examples. Okay, let's find the end behavior and the y-intercept of this guy. So to first find the y-intercept, what do you have to do? You have to plug in 0 to the function. So that's going to be 2 minus 3 to the 0 power. 2 minus anything to the 0 power is 1. 2 minus 1 is 1. So if you plug in 0 to this, you would get 1. So this is the output 0, 1. There's the y-intercept there. Okay, the end behavior. As x goes to infinity, what's the function going to do? Okay, well, as x goes to infinity, we'd have 2 minus big. So big gets bigger. So 2 minus infinity. Well, 2 minus infinity, this is essentially going to go to negative infinity. right? Because it's going to be 2 minus 9, then it's going to be 2 minus 27, then it's going to be 2 minus 81. Okay, it's going to keep going big negative. So 2 minus big, this is going to go to negative infinity. As x goes to negative infinity, f of x is going to go to, okay, well, big numbers get bigger if they go to positive infinity. Big numbers get smaller if they go to negative infinity. So this piece here is going to go to 0. Right? So 2 minus 0 is essentially what we would then have. That's going to equal 2. So basically this piece over here is all going to go to 0. 2 minus 0 is 2. Okay? Because again, as if you have a number greater than 1 and you take it to a large negative number, for instance 3 to the negative 5, remember that is equal to 1 over 3 to the 5th, okay, which is a really small number, and then 3 to the negative 6, that is equal to 1 over 3 to the 6th. See how these are just going to keep small, 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 small? So 3 to the x, when you plug in negative numbers and large negative numbers, is going to go really, 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 really little. So this whole thing is basically going to go to 0, which would leave us with just 2. And that's the end behavior here. Okay, what about the end behavior of this guy and the y-intercept? So the y-intercept is plug in 0 to the function. So 1/3 to the 0 minus 2. Anything to the 0 power is 1. 1 minus 2 is negative 1. So this y-intercept would be at 0, negative 1. What's going to happen as x goes to infinity? Well, as x goes to infinity, 1/3 to the x, as x gets really, 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 really big, that means we're constantly going to be like, take a third, take a third, take a third, take a third. We're going to cut, 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 cut. So after about infinitely many cuts, this whole thing is going to go to 0, which means we will essentially have 0 minus 2, which will equal negative 2. So as x goes to infinity, our function is going to go to negative 2 by this logic here. As x goes to negative infinity, what's going to happen to 1/3 to the x now? Well, this is essentially going to be 1/3 to the negative x, which is equal to 3 to the x by the negative exponents property. What is that guy going to do? That guy is going to go to infinity. Okay? And what is infinity minus 2 going to be? Oh, it's still going to be, this is essentially, okay, well, what is infinity? Because that's going to go to infinity. Well, what's infinity minus 2? Well, that's still infinity. So f of x is going to go to infinity. The graph of this, so 0, negative 1 is our intercept here. As x gets really large, we kind of bottom out at negative 2. And then as x gets large, negative, we shoot up to infinity. So that's what the graph of that would look like. Okay? Just remember, exponentials, small numbers get small, large numbers get big. Whether they get big negative or they get big positive. Okay? But they're either going to go to positive infinity, they're going to go to negative infinity, or they're going to go to 0. And then you just kind of play with whatever back number you have here afterwards. So, back to that Lorax guy. Okay, well, how many trees were in the forest to start then with this function? Okay, well, how many trees were in the forest to start? Well, let's plug in 0 here. Okay, anything to the 0 power is 1. So t would equal 1250. So the Lorax was dealing with 1,250 trees when he started. Okay, and the next question was, after many, many, many days had passed, so as x goes to infinity, where is t going? Okay, well, this is a small number, so exponentials say small numbers raised to infinity are going to go to 0. 0 times that, ooh, that's not good. T would go to 0. So if the Lorax does absolutely nothing and says, screw this, I'm done with these tuffula trees, his forest would get decimated. So luckily, as you guys know from the story, he does not do nothing and comes in. Perfect. So here's the graph. This is